live. Can you both hear me? Vic, can you hear me? Good. AT, can you hear me? All right, good. So we're starting with let's move. We're going to quickly do all the science chapters and all the math chapters in 2 weeks. I'll make sure we are done by the end of July. That's a big target, and let's do it. So we start with here, chapter 5. This is for science, and let me just remind you so that I see that you remember. Remember that for our chapters we have chapter 1, chapter 4. Let me put it like this. You have 3 chapters for bio. You have 3 chapters for chem. You have 3 chapters for physics. For bio, it is chapter 1, chapter 4, chapter 7. This is chapter 2, chapter 5, chapter 8. This is chapter 3, chapter 6, and chapter 9. We are doing chapter 5, which is called reactivity, and it is for chemistry. So the chapter we are doing is in the 3 chapters for chemistry. Our science, this is what we call stage 9 science. This is our checkpoint, stage 9 science. It has these 9 chapters. We are doing chapter what? What chapter are we doing right now? Quickly tell me. Hello? What chapter are we doing? We're doing chapter 5. Yes, well done. Which is reactivity. Let's go for it. Let's understand. So when you're done with the chapter, you need to know 5 parts. When you're done with this chapter of reactivity, you need to quickly know 5 parts, which is number 1, reactivity. What is reactivity itself? And what is the reactivity series? Okay, reactivity and the reactivity series. Then when we are done with it, we go to the second part, which is what are displacement reactions? We quickly study them. Then we study how do we make salts. Then we study rearrangement of atoms and energy changes. This is small. The last 2 things, very, very small. So you should know reactivity and reactivity series of metals. So we are studying reactivity in this chapter, and we are studying the reactivity of metals. Right. So let's go for it and let's understand. Now, here's the chapter. What everybody should know when we are studying this reactivity. You should know that there is a pattern that is followed by chemical reactions, and we will need to know it, especially when we get towards the end of a chapter. Towards the end of the chapter, we need to know this pattern. You should know that when you have substances react, remember we are studying reactivity. We are studying reactivity. Which metals react more than the other ones? Now, when you have metals react, we are going to need you to know that 2 things happen. Atoms rearrange and energy is released. So when we have a reaction, the atoms rearrange. Did you see this word? What happens to the atoms when you have a reaction? What happens to them? They rearrange. That's a key word. Are we together, Vic? Do you see this? The atoms rearrange. Well done. And we have energy being released. So you should then say energy is released. AT, do you see these 2 important things? We'll see what happens when energy is released. All right, good. So from there, we'll talk about everything else. Now, when we talk about reactivity, we are studying reactivity of metals. So let's quickly go through it, okay? Then we'll see displacement reactions and stuff. Reactivity is the foundation of the entire chapter, the reactivity series. Like I said, when you are studying reactivity of metals, we just need you to remember the list, the reactivity series of metals. Which metal is more reactive than the other? Is it potassium? Is it sodium? Which metal is more reactive than the other. So here's how you should remember it. Okay, let's start by the definition. When you study reactivity, if they ask you define reactivity, you say reactivity is how easy it is for a substance to react. Reactivity is how easy it is for a substance to react. When we say something is reactive, it means it reacts easily. It reacts easily. That is a reactive metal. A reactive metal reacts easily. Okay? This is a more reactive metal. When you have a lower metal, it's not as reactive. It's less reactive, which means it reacts less easily. Once you see the word reactive, it is how easy is it for this thing to react. How easy it is for something to react. That's reactivity. Now you must know this reactivity series of 9 metals, and you should remember it by having this mnemonic. You must know it. It's important, and I'll show you the reactions you can get. You must know this reactivity series. Please stop calling my zebra. Instead, collect silver and gold. Okay? But and represents nothing. Please stop calling my zebra. Instead, collect silver and gold. Did you see it? Please stop. We'll make it longer when you get to IG. We'll say me a cute zebra. But here you just say, please stop calling. You don't say me. You just say calling my zebra. Instead, you should collect silver and gold. Please is potassium. This is the highest metal in what we call the reactivity series. And when metals are high, they are the most reactive ones. The most reactive ones are found at the top, and the least reactive ones are found at the bottom. The ones at the bottom are the least reactive metals. So you gotta know this, that the metal at the top of your reactivity series is the most reactive one. In this case, it's potassium. So please represents potassium. Please stop sodium. Calling, so stop is sodium. You should do it fast. You should write it fast. And sodium in chemistry is Na. Then the symbols are not from their English names. So this is not its English name, Na, but we use that as the symbol. Potassium, K. Sodium, Na. Calling is calcium, Ca. Magnesium. So we want to see the yams. Potassium, sodium, calcium, magnesium, Mg. Then you get to zinc. Here, zinc. Here, iron, Zn. Iron, Fe. Copper, silver, gold. Zinc, iron, copper, silver, gold. Copper, Cu, silver, Ag, gold, Au. These are all the elements in the reactivity series that you, as a Form 2 or Stage 9 student, should know. Okay? You don't have to know carbon. You don't have to know hydrogen. Are we together, students? But what I want you to know is that if you had carbon, it would be here. You should just know, because we'll talk about it so that you know. If you had carbon, it will be after the yams. Okay? Are we together? It will be after the yams. So put this. It's important. We'll talk about it. But I want you to know, please stop calling me. Please stop calling my zebra. Instead, collect silver and gold. Say it so many times. Can you say it? Victor's on. Say it real quick. Mm-hmm. Instead, what? Good. 80. Yes. Collect silver and gold instead of calling my zebra. Right. Now, here's what you should know about the reactivity series that I want you all to know is that the metals that are higher are the higher you are, the more reactive you are. So if I come and I ask you, Victorson, which one is more reactive, zinc or iron? Which one is more reactive? You tell me, sir, the more reactive one is zinc. Well done. Well done, I agree with you. Because it is higher. So simple, the higher you are, the more reactive you are. So we need you to write this so that you can now compare and see which one is higher for the times when you are going to be doing reactions. So higher metals are more reactive. In other words, they react more easily. Lower metals are less reactive, which means they react not as easy. So that's important. You will always come and check the position of your metal on the reactivity series. So you must be able to make one. They can ask you to finish up a reactivity series. They'll give you one which has missing spaces. Be ready for that. We'll go to questions just now. Now, this is reactivity series of metals. Okay, we don't do of non-metals. We only do of metals. So this is the reactivity series you must know of the metals. Then, what you should know is that we are done with reactivity series. We now know the order of the metals from strongest or from the strongest to the weakest. Who's the most reactive? Who's the least reactive? We now know the order because we now know the reactivity series they expect us to know at our age. Now, after knowing it, you must then know something else, which is this, which is how do metals react with oxygen, water, and acid, dilute acid? All those metals on your reactivity series, if they react with oxygen, what will they form? They will form the same things if they do react with it. If they ever react with water, if any metal you saw on that reactivity series, if it does react with water, it depends on its reactivity. But if it ever does, it should form the same thing here. And if it ever reacts with an acid, a dilute one, okay, we reacted with a dilute acid. If it ever does, then we should get it. Are we together? When a metal, anytime you are going to get a metal on that list, if it ever reacts with oxygen, you must expect only one product, which is the metal oxide. If metal meets oxygen, we expect only one product, which is going to be the metal oxide. So if we have sodium meeting with oxygen, then you can have what? Sodium oxide. Okay, so we can even put 4 of them here and put 2 here. This is what happens when metal meets oxygen. You get metal oxide. You get metal oxide. Don't let me down. You get one thing, metal oxide. You must know it. If I ask you randomly, hey man, what do you get when metal meets oxygen? You should tell me you get metal oxide. Let's quickly move on to the next thing then. What about when metal meets water? Now, this water could be steam. Steam, which means gaseous water, not the liquid water which you guys see. It could be steam, or it could also be liquid water. So it depends with how reactive the metal is. But what I want you to say is that if it ever reacts with water, it should give us 2 things. So now you are dealing with water and you are dealing with an acid. You will now be getting 2 things. Okay. Dilute acid or water, you are now getting 2 things. You are now getting 2 things. For our metal and water, you get a metal hydroxide, which means it will be a metal and it ends with OH, like sodium hydroxide and hydrogen gas. I'm going to show you how, but I want you to tell me if you're asked for water, you don't get an oxide, you get a hydroxide and you get hydrogen. For acid, you get hydrogen again as your byproduct with a salt. A salt just means metal bonded with a non-metal. A metal bonded with a non-metal. For example, to say sodium chloride. There we have. This is a salt. A metal and a non-metal together. So anyway, remember, hydrogen will now always be given also. But for when you meet with water, it's a metal hydroxide and hydrogen. But when you have metal with an acid, it is a metal, it is a salt, but plus hydrogen, if I can say that. It's just a salt plus hydrogen. Have you seen this? Students, have you seen this? Vic, are we together? Good. So let's do it together right now. Let's see. What do you get when you say metal plus oxygen? If the metal you are dealing with has the power to react with oxygen, if it is reactive enough, then what will you get? What do you expect to get? When any metal reacts with oxygen, what do you expect to get? Tell me. Metal oxide. Right? Just one thing. Well done. What about if you have metal now meeting water, which could be your steam or your liquid water? Metal, you are now meeting water. You're now meeting water and it's reactive enough. What will you get? If you put sodium in water, I remember showing you, it will be a flame, it will be a fire, and it will be forming something. What is being formed, Mr. AT? What is being formed? Metal what? Metal hydroxide. Yes. Plus what? Plus what? What do you always get now? Well done, Victorson. Plus hydrogen. You always get hydrogen now at the end. as a byproduct. It's another product. What about when metal meets an acid? Okay, what do you expect to get? When a metal meets an acid, what do you expect to get? Yes, what do you get? Here, what do you expect as your byproduct? What should always be the byproduct here? Say, yeah, hydrogen, right? And then here, what will we have now? Salt, which means metal plus non-metal, right? Have you written? These are, you should say, so far, you understand the reactivity series. You know who is more reactive. You can write it. And you should also say, you also know the 3 fundamental reactions of metals. The 3 important reactions of metals. These were the ones that were used to make the reactivity series. But you don't have to know that too much. You do at IG. You have to know. But here you need to know the 3 important reactions of metals. Are we together, 80? The 3 important reactions that all metals that do react, if they ever react, they should give you these. So it would depend on the power of the metal. But if it has the power to react with oxygen, then we know what it will give us, metal oxide. If the metal you have has the power to react with water, we know what it will give us. It will give us a hydroxide plus hydrogen. If the metal has the power to react with an acid, it will give us salt plus hydrogen. That's it. So are we fine on this first section? Are we fine on the first section? We must be fine. What should we know in the first section, sir? You should know the reactivity series, and you should know the 3 important reactions of metals. You must know them. Then now you come to the second section. It is now you applying the knowledge. You know now, so you got to apply the knowledge. You study what we call displacement reactions. Displacement reactions of metals. This is what we are studying now. Displacement reactions. What is to displace? You should show us you understand English. To displace is to remove and put something else. Oh, they've been displaced. That means they have been removed. When we do a displacement reaction of a metal, that means you have one metal removing another. That is what we call by a displacement reaction. This metal has been displaced. It has been displaced. It has been removed. So when you move something, that's displacement. When you move it, like when you move it from a position. Now, when you are dealing with metals, what you must know, here's the key thing. Now that you know what displacement means, so when you do displacement reactions, you're expecting some metal to remove another. Really? Can one metal remove another? Yes. How does that happen? You should know this. A more reactive metal replaces or displaces a less reactive metal from its compound. A more reactive will remove a less reactive from its compound. For example, if you go to the reactivity series, you will see that sodium is more reactive than magnesium. Or let's say potassium is more reactive than sodium. So if potassium meets sodium, and sodium is in a compound, this is a compound, it's a salt and it's a compound. Why is it a compound? It has two or more different elements, sodium and chlorine, so it becomes a compound. If potassium meets this compound, it is more reactive than sodium. It is higher on the reactivity series, so it will displace. That's the rule. So sodium, you gotta go, sir, and you're gonna have potassium taking the chlorine. And now, oh shame, sodium is now out there alone. This is what we call a displacement reaction. Are we together? Higher metal will displace the lower metal. The lower metal can never, it will never displace a higher one. If we say, can sodium displace potassium in here? That is not going to happen. Sodium cannot remove potassium because potassium is more reactive. So this is no reaction. A lower metal can never displace a higher metal. Are we together? Are we together? Good. Vic, are we together? Okay. Right. Now we come to here. Look at this. You'll be having this displacement reaction, whatever. You'll be having these displacement reactions. In here, copper is lower than zinc. So it cannot remove zinc. It can't. It's lower. It's less reactive. So lower ones can never remove higher ones. Never. There will be no reaction, but a higher one will always remove a lower one. Now, when a displacement reaction occurs, you should see something to show that a reaction has happened. Because it's a reaction. You must see something. Either you see the temperature now beginning to rise, okay, the temperature of your solution, or you see the color changing. So, because a new substance will be forming, obviously, so the color changes. The color can change. Or you can see metal coating. The less reactive metal, it is going to go on the surface of the more reactive one because it has been removed. These are all things that can happen. Or you can see the more reactive metal disappear. So these are observations, things that you can see with your eyes that will happen in this situation. Right. Are we all fine? Okay. So now, this is why I showed you where carbon is. Where did we say carbon comes? On the reactivity series. We said, where do we see carbon? After which ones? Where do we see carbon in the reactivity series? After which ones? After? No, I want you to use what we said. Where do we see carbon? After the yams. Do you remember? We see them after the yams. Yes. After the yams. after magnesium, potassium, all these, after these yams, the guys that end with yam, 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 then we are going to meet carbon. Now, I want you to know one thing. Listen closely, everybody. Listen closely. Right. Carbon can be used to remove things that are below it. Because the higher you are, the more reactive you are. So carbon is more reactive than these guys. So carbon can be used to remove these, to extract these. Are we together? Carbon can remove all those that are less reactive than it, because they are less reactive. Now I want you to say, what is to extract? Because there is no one who's mad. We don't have mad people here. We can't just tell you that we extract when there's nothing to extract. Let me tell you right now, if you see this diagram, you are going to see how most metals are found. Even gold itself. Most metals are found as rocks. Most metals are found as rocks. The good thing about gold is it's not reactive. So it will not react with things, but it will be just needing to be cleaned and stuff. But other metals, a lot of these other metals are found as what we call ores. An ore is a rock. So you can have some serious mining companies mining some of these rocks here. Mining some of these rocks here that you are seeing. What you must know is that any metal that is below carbon, when we extract it, we extract what is to extract. To extract means you want to remove the metal from the ore. When we say it's a rock, that means it has other things that are not metals here. And we're going to need to remove them. That's extraction. It's removing the metal from everything else so that we have the metal. And we do it using carbon for all the things. Are we together? All the things below carbon, we are going to remove impurities. We are going to make it a pure metal. We are going to separate it from the unwanted things in the ore. So instead of having just a rock, we can have a metal, a pure metal. And that's what we call extraction. So when you go underground to look for metals, you will not find them as bars. You will find metals underground as rocks. And when they are rocks, we call them ores. They have impurities that you're going to need to remove. And if the metal is below carbon, you use carbon to remove those things, because carbon will displace the metal. Let's say you have metal plus some unwanted things, especially oxygen it could be. So it'll be metal oxide. Then you meet carbon. Carbon is going to say, hey metal, I'm more reactive than you. Let's say you're doing the metals from position 5 up to 9. Metals below carbon. If you meet it as an oxide, say, hey, it meets carbon. Carbon will say, hey metal, get away from there. And carbon will take. So it'll be carbon plus the metal. So the metal has been kicked out. It has been displaced. But guess what? We will be happy. We want it to be displaced so that we can have it as a clean metal. We will now collect it. Right. So this is what happens. Don't let me down here. And that is what I've shown you here. Where is it? I've shown you here to say, if a metal is below carbon, then you extract it. In other words, you separate it from its ore by adding carbon, so by carbon reduction. Then you have metals above. These ones are done by electrolysis. You don't have to know it right now. You know it at IG. Electrolysis, how we use electricity instead of carbon. We'll be using electricity. But it's for the strong ones, the ones above carbon. But if we are below carbon, then we are going to use carbon. Look, this is exactly what I gave you. The example that I gave you. I put it again in here. Metal oxide plus carbon. You say if the metal is from position 5 to 9, which means it's below carbon, then we know what will happen. Carbon will say, hey, get out of there. Leave the oxygen alone. Get out of there. And it will take the oxygen and become carbon dioxide and leave the metal. Are we done with this displacement reactions and how to extract metals? Now we are. Good. Now we are going to this section, which is salts. This is important. A salt is produced when an acid reacts with a metal or metal oxide or carbonate or alkali. So when acid reacts with these, we will get a salt. But obviously, the most important ones are metal and metal oxide, because we are studying metals. So if an acid reacts with a metal or metal oxide, so here's what I do. Remember that when we say the nice definition, we say it is whatever is produced when acid reacts with metal. That's a salt. But remember, a salt is just a metal with a non-metal together. An ionic compound, which means metal and non-metal together. We call that a salt. We call that a salt. Now, is this a salt? Yes. Why is it a salt? Because it's metal and non-metal. And this is actually the salt we use for food. Table salt. What about this one? Is this a salt? Yes, it is. Why? We have metal, magnesium, non-metal, chlorine together. Can you all see? So when we have our salt, it is when you just have a metal bonded to any non-metal you know. You are going to have a salt. What about this? This is called ammonia. Is it a salt? You say, no, it's not a salt. Why? There is no metal. Nitrogen and hydrogen are both non-metals, so it's not. So a salt is going to be metal and non-metal together. Now, let's see how we name these salts. A metal plus non-metal together. Let's see how we name. We're going to talk about the salt making. But let's see how we name them. Can you see? So, the acid that it comes from here will be the end of the name. The first part, remember, a salt is going to be metal and non-metal. So the name will have two parts. First, you must know this non-metal you have, what acid did it come from? If you know the acid that the non-metal came from, then you will be able to name the salt. For example, this chlorine always comes from hydrochloric acid. So, if it comes from hydrochloric acid, then that salt that you form will always be a chloride. Are we together? So this will be sodium chloride, because you have chlorine that came from hydrochloric acid. So if you want to know, the first part of the name is easy. It comes from the metal. But the last part will come from which acid is it coming from. So when you come from hydrochloric acid, your name will end with chloride. You should know these three important acids. Hydrochloric acid, sulfuric acid is H2SO4. Nitric acid is HNO3. Can you see this? What you then know is you look at the acid. You should know nitric acid. You should know its formula. So when you see it, and any salt it will make should end up with nitrate. You should know sulfuric acid, and any salt it should end up with sulfate. You should know hydrochloric acid, and any salt it should end up with chloride. Are we together? So when you when you want to name your salt, look at the acid it came from. Is it a sulfate or nitrate or chloride? It will be one of the three. Are we together? Have you mastered naming? The first part comes from the metal, which is there. But then you have to check the acid. Now we go to this. Now that you know how to name, we go to this. The methods of making a salt. When you want to make a salt, you should just know who should you react your metal with. Here, you take your metal, you react with an acid, you will get a salt. Or you can take, instead of metal, you can take your metal oxide, you react with an acid, you will still get salt. When you have now a metal oxide and an acid, you will still get what? A salt. And instead of hydrogen, you get water. So can you please all make sure you know these, especially these first two. You should know this reaction, these ones. Acid plus metal gives you salt plus hydrogen. Acid plus metal oxide gives you salt plus water. This is a very important table. Very important. Now, what I can also tell you is the last two methods, which you should then know after this, is when you have a carbonate. A carbonate ends with CO3. It will be something, something, CO3. If you have a carbonate, or if you have an alkali, we'll talk about them later. You will also be able to react and get a salt, which means metal plus non-metal. You will also get a salt. But you won't just get a salt, you get salt plus water plus carbon dioxide. This is important. Just note these reactions. I'll give you more later. Let me see what the last part. This is your chapter is almost done. Okay, it's almost done. I just want to show you something. Then we'll come back to this. Let me show you. We have to finish the part. Oh, there's something I want to show you. Wait. Give me one second. Where is it? Where is it? Okay, it's here. It's on this page. You should now know the difference. After knowing how to make a salt and how to name them, you should know the difference between a base and an alkali. Alkali is a soluble base. A base is all of them together, the soluble and the insoluble. They are called bases. If you just take only the bases that are soluble, remember there are bases that are soluble and bases that are insoluble. If you take the bases that are soluble, you now have an alkali. So an alkali is just a soluble base. This is it. Alkali represents a soluble base. Are we together, AT? AT? Alkali represents what? What is an alkali? Yes. It's a what? Which is a special type of base. Yes, which is what? Exactly. A base which is soluble. Exactly. Every alkali is a base. But it's a base that is soluble. Not all bases are alkalis. In other words, we are saying not all bases are soluble. That's important. Make sure you know that. We're going to talk about it later. These separation techniques, I'll teach you. When we say we are doing a separation technique, when we have filtration, we'll be trying to take all the insoluble substances. Things that are insoluble, they are the ones that are caught on the filter paper, and they are going to be left behind, and we'll call them residue. Anything that dissolves in water, it will never be filtered. It will pass through in the solution. So filtration is only to get the insoluble substances. All right. So you should know these words: residue and filtrate. Filtrate is not found on the filter paper. It passes through back into the solution. Residue is going to be the please remember this. Filtrate passes through. Residue is filtered out. All right. Now we go to the last two ideas and you're done. You've done reactivity, you've done salts and everything. Now what you must then know is what we talked about when we talked about rearranging. What happens when a reaction happens? The atoms are rearranged. And then what will happen? Energy. You'll be having energy released or whatever. So how do you have atoms rearranged? Whenever a chemical reaction happens, the atoms will just rearrange. They are not created. They are not destroyed. You don't make new atoms. Don't let this be in your mind. A reaction does not create new atoms. It just rearranges. You get new combinations. You get new products. That is what happens in a reaction. The same atoms that you had are rearranged. That is what you have. Right. This leads us to this. Conservation of mass in a reaction. What you must know is that when you are going to deal with a reaction, remember, you are not creating anything. The atoms are just being rearranged. Iron, this atom is taken from iron. It was in the iron, it is now put together with this. There is rearrangement. And we get a new thing. But we did not create anything. And we did not destroy anything. The magnesium was put to be with oxygen. They mixed them up. They rearranged. And we get a new thing called magnesium oxide. Now, what you must remember is that mass can never be destroyed. You cannot destroy mass. So, if we have a closed system, which is a system where you can't have anything escape, a system where no mass is lost. In a closed system, what you must know is that if you have a closed system where nothing is escaping, then what we already know is that we cannot create new mass. We cannot destroy mass we have also. So the mass should stay constant. So what we know is if we have a closed system where nothing is escaping, what we know is that before the reaction, the total mass should be the same as after. So we will have new products, but this mass here before should be equal as this mass after. They should be equal if only if it is a closed system. In other words, if we are not allowing things to escape, then the mass before the reaction should be equal to the mass after. This is a law. The law of conservation of mass tells you that, Mr. Man, you can't create or destroy mass. The total mass before a reaction should be equal to the total mass after. But if we now have an open system where gases are allowed to escape, here you will have the gas escaping, and it will look, what you should know is that the mass before will no longer be equal to the mass after. You say to me, really? Yes. So does it mean that mass has been destroyed? Where did the mass go? It has just left. The gas has just escaped into air. But it has not been destroyed. The mass will decrease, but it has not been destroyed. It will decrease because the gas has escaped, because it's an open system. Are we together? What about when you burn? Here is something very important. If you take a rock, if you take magnesium, the rock, and you burn it, to burn it means to react it with oxygen. Okay? You get 2 of magnesium oxides. So what you will see is that it will look like this rock of magnesium has increased in mass, because there will be more here, but it hasn't increased in mass. It has just reacted with oxygen from the air. So the oxygen from the air will come into the system and add to the mass. But nothing was created. So this is important. This is from the air. So it was not there in your vessel. So when you were measuring the mass, you were measuring mass of magnesium only. But after burning, you get magnesium oxide, which will have more mass than this magnesium when it was alone. Now, what about energy changes? We saw that in a reaction, atoms just rearrange. What about in a reaction? What happens to energy? In a reaction, either energy is released or energy is absorbed. So atoms are rearranged and energy can either be released, that is exothermic reactions. Exothermic reactions are reactions that release energy. So exo is to exit, is to release energy to the surroundings. So if you go close to that reaction, you will feel warm. It's like the burning of magnesium. When you are burning things or combustion, it just means burning. When you are burning these metals, in other words, when you are reacting them with oxygen. So this is what will be an exothermic reaction, a reaction which releases energy to the surroundings. On the other hand, when we now say entering, it's a reaction that absorbs energy from the surroundings. It takes in energy from the sun. So when you go to it and you feel it, it'll be feeling cold. You will feel cold. It's because it's taking the heat. So you should remember. And instead of combustion, endothermic reactions. These are just reactions that you need to heat for them to start. They absorb energy. So I want you to say, don't forget, there are energy changes in any reaction. You can't have a reaction which will do neither of the two. That's a lie. Because in a reaction, atoms are rearranged and energy is transferred. So if you have exo to exit, that means energy is transferred from the reaction to the outside. So it's a reaction that releases energy to the outside, exothermic. And because it does that, the temperature of the outside will be rising. It will be becoming hotter. Endothermic, here, instead of heat exiting, heat enters it. So it absorbs, it doesn't release, it absorbs or takes in energy from the surroundings, and the temperature of the surroundings will fall. You get to this reaction, you feel outside of it, it will be cold. It will be in a beaker, you feel the beaker will be now feeling cold. It's because it's absorbing. Don't worry about the practicals. We'll talk about all the practicals in one lesson. Not now. Right, these are the important things, and you are done. Let's see the let's see some important questions that I gave you. And they'll make more sense when you do notes. You write them down. When you have zinc added to copper sulfate, what do you observe? So let's try. Let's see if this will work. Zinc plus copper sulfate. Will we have a reaction here? Will we have a reaction? Well, which one is higher on our reactivity series? It's zinc. We'll go back to our reactivity series, but zinc is higher. Please stop calling my zebra. That's zinc. Instead, should what? Collect silver and gold. So to collect, that's now the copper. Copper is lower than zinc. So it will be booted out. To be removed, you are going to get zinc sulfate plus copper. displacement reaction will happen. Now, what do you observe? You will observe, remember, either when we said observe, we said either you will see a color change, or you see the more reactive metal disappear, or something. Here you should know that you are going to have copper sulfate, which is in waters. It's called hydrated copper 2 sulfate. It is blue. So that blue will go. Why is the blue going? It's because copper sulfate is going. We now have zinc sulfate and copper. Right. So this is important. What do you see when zinc is added to copper sulfate? You observe a color change. Okay? From blue to colorless. Name the salt produced when hydrochloric acid reacts with zinc. Zinc plus hydrochloric acid. What did we say? We said the first part will be zinc, then the last part will be from the acid. If it's nitric acid, we said it will be a nitrate. If it's sulfuric acid, we said it will be a sulfate. If it's hydrochloric acid, we said it will be chloride. So this will be zinc chloride. State the gas produced when a carbonate reacts with an acid. All right, we talked about it here to say when you're going to have, these are the reactions that form your salts. Acid plus carbonate. This is pretty much the same thing as acid plus metal oxide. You will get salt. Instead of salt plus hydrogen, you say salt plus water. But then you say plus carbon dioxide because it's a carbonate it added. So you get salt plus water plus carbon dioxide. And what is carbon dioxide? It's a gas. I'll teach you how to test for it. How to test for carbon dioxide. Right, so here. A student burns magnesium in a closed container. Will the mass change? No. The mass stays the same because the atoms are just rearranged and nothing is created or destroyed. So it's a closed system. Nothing is escaping. The mass stays the same. You burn magnesium in an open container or an open system. What happens to the mass? What will happen to the mass when you burn? It will increase because the oxygen from the air is coming into this container. So you're going to have the mass appearing to increase because magnesium combines with oxygen from the air to form magnesium oxide. So that's a good day. That's a good day. That's a good thing. Describe how you would obtain pure crystals of copper sulfate from copper sulfate solution. Now, crystallization, what it just means is we are going to make something be a solid. So what you do is you heat it until the water is gone. You heat gently until almost all the water is gone. You leave just a little bit of water. You should start to see the solid forming. But don't make all the water go because you end up burning your copper sulfate. It will start melting. So you heat until almost all the water is gone. Then you filter the remainder. So you now take, there's still some remaining water. So you now come and pour it in here. Then you are going to have your solid remaining, the solid that you wanted. It will remain here as the residue. Don't forget here, you're going to have your residue. Then the water will just go on and collect at the bottom as the filtrate. Now this residue, the solid you remain with, you put it out to dry. When you put it out to dry, you'll be getting crystals. And you now have your copper sulfate crystals. All right. That's it. You've done very well. Maybe let me just give you the 2 gas tests that you must know. You must know that when you are testing, this is the last thing. Listen. When we test for, there is oxygen, there's, maybe I should put oxygen. Oxygen here, we use a glowing splint, which means a splint is just a tiny piece like this. This is called a splint. So if the splint is burning already, you light it, it starts to burn. If you put it inside hydrogen, you take that splint, you put it inside the gas that you don't know. You don't know what gas it is. Is it hydrogen or what? If you want to check if a gas is hydrogen, you light your splint up to start burning. You light your splint up. This is the splint. You light it up. If you put it inside hydrogen, you should start to hear. It should have a squeaky pop sound, which means that it is in hydrogen. You would have tested, you would now know, that means this is hydrogen. Because hydrogen is the only gas that can make a lighted splint make a pop sound. It burns with a pop sound. Hydrogen burns with a pop sound, so you can do it. Just use a splint. If you want to test if something is carbon dioxide, you use lime water. When you mix carbon dioxide with lime water, the lime water should go milky white, like milky white, whitish. Instead of colorless, it will become whitish. So carbon dioxide, it turns lime water milky. Oxygen, you put a glowing splint, which means a splint which is no longer burning. It's just red, like a cigarette, but it's not burning. When you put it inside oxygen, it will be relighted. That means the fire will start burning again. So oxygen can make a fire burn again. You put a glowing splint in there, it should start burning again. Any questions? Any questions? A splint, it's a small piece of wood like this. A tiny, thin, when you take a small piece, like a tiny one that you can use. So you should know these gas tests. You should practice them. You should know them. Are we together? Okay. Right. Now I want to see how you've heard me, how good you are at this chapter. I want to give you question after question. Let me give you right now. I want you to start writing right now and you submit. Then we do the next thing. Okay?